Afternoon. I'm Scott Case, and we're going to have some fun today. Is anybody here having fun yet? Raise your hand if you're having fun. Okay, good. All right, so I'm Scott Case. I'm the founder of Zettawatts, which is a new startup. We're the creator of something called the additionality REC market. And additionality RECs are forward contracts to buy RECs from new projects that haven't been built yet. So raise your hand if you have Scope 2 emissions and you think that buying RECs are good enough for clean energy. Good, nobody raised their hand. Come see me afterwards because we have a better product for you. And I'm absolutely delighted to talk to our panelists today because they are like super geniuses. I barely belong up here with the level of brilliance that they have. So first we're going to start with Rachel Slaybaugh, who is a partner at DCVC, where she's focused on climate sustainability and energy investments. Rachel was an associate professor of nuclear engineering at Berkeley. I just want to let that settle in for you for a second here. I know there were rocket scientists talking before. Rockets are a different problem. Nuclear energy, no joke. Lawrence Berkeley National Lab, where she worked on the cyclotron road division. And as a side hustle, she was a program director at the Department of Energy's ARPA-E, focused on their nuclear fission program. So if you thought your side hustle was like really hitting it hard, just know that Rachel can one-up you a little there. And then we have Matt Gray, who is the co-founder and CEO of Transition Zero. Matt's an energy market analyst with more than a decade of sell-side and consulting experience. Prior to Transition Zero, Matt was the head of European carbon and power research at Jefferies Bank. And he's also done a stint at the International Energy Agency and was the managing director of the power and utilities team at Carbon Tracker. So welcome. We're super glad that you're here. I'm going to start with you, Rachel. Can you give us 60 seconds on what DCVC does and where you're throwing money right now at things?
Sure. So DCVC is a deep tech firm. We've been around for about 12 years. Deep tech means we do things with real scientific complexity. We're not afraid of hardware. They often have a significant computational and data component so that as you operate the business and get more data, the technology improves and the technology advantage improves. We invest in a variety of sectors, including climate at the seed and Series A stage, and we invest in climate specifically at Series B and beyond. So I cover climate there. We do all kinds of things, including energy transition, clean water, basically anything in the carbon mitigation, prevention, and to some extent climate change adaptation space.
Awesome. And Matt, tell us about Transition Zero and what you're totally fired up about right now.
Great. So Transition Zero is a mission-driven company. We're very new, only a couple of years old. And what we do is we provide energy systems modeling as a service. For those of you who don't know what energy systems modeling is, it is a tool to understand and plan for the energy future. So for example, when an investor wants to know where to put a solar farm or a wind farm, or when a company wants to understand a procurement strategy for meeting their net zero target, they tend to use energy systems modeling to inform those decisions. Current energy systems models are closed and costly. We are different. We provide energy systems models which are accessible, auditable, and reproducible. And the reason we do that is we're trying to create a global data standard for energy transition planning data.
Awesome. All right, cool. So before we get into it, you heard Bill Gross talk a little bit about the progress that we have made. We're going to spend a little bit of time talking about the transition to a clean electricity future. So we're going to narrow it down to just the electricity piece of it. And just keep these things in mind. So number one, we've got to swap out all the fossil fuel generation that we have today. The second thing we have to do is we've got to electrify everything that currently uses fossil fuels. And then because we do that, we have to generate even more electricity because we have to make up for the fact that we electrified the shit out of everything else. So then we have to figure out how to navigate interconnection queues and the transmission part of the grid and the distribution part of the grid. And on top of that, we've got to tackle what amounts to base load, which is hey, it turns out that we use electricity 24 hours a day, not just when the sun's shining and the wind's blowing. What are we going to do about that problem, which is right now filled by coal, natural gas, and nuclear. And nuclear is our secret weapon in some ways here. But we've got to solve all those problems. So the good news is we have 15 minutes and 15 seconds to solve them all. So it's going to be great. It shouldn't be too hard a problem. We got a nuclear physicist and a data guy with us, and we're just going to sort it all out. If you all could just take notes, you just have to do all the things we're going to talk about. So we're just going to outsource this to all of you to get it done. Exactly. Well, our bank account information will be up on the screens. Just the wiring and for instructions will come up later. So with that in mind, Matt, there's like 4,000 gigawatts, okay, of fossil fuel generation on Earth. That's like thousands and thousands of plants everywhere, right? Like all across the globe. How do we prioritize which one of those plants we ought to be like focused on taking offline to have like the greatest impact? Because we've all seen that SBTI curve, and so like we've got to keep marching down that curve, and it gets in some ways harder and harder and harder as we get closer and closer to the bottom there. So like, how do we use data and be a heck of a lot smarter about doing that?
Yeah, well, I think there's two ways. There's the financial component, which is working out the age of the asset, the extent that it's been depreciated. Obviously makes more sense to retire the oldest units first because they have paid back their capital and there's not that stranded asset risk. Whereas if it was a new asset and if you're retiring it, that capital will be at risk and there would be stranded assets as a consequence. But then there's also the economic component, which is what role does that asset play in the electricity system? What contribution is it making to ensuring that supply is meeting demand at all points in time? And that is the unique thing about electricity markets, is the system always has to balance. There always has to be electricity available. And I think that's where you really have two options. You can replace that coal plant or that gas plant with all the cool stuff that Rachel will talk about and that Rachel's investing in, or you can use energy systems modelling analysis to understand if you take that plant offline, what will you need to replace it with, and crucially, where will those assets need to be geospatially to ensure that that supply gets to demand when it needs to.
So you talked a little bit about, and you referenced, Rachel, about sort of the nuclear piece of this, right, which again plays a big role in that baseload part of it. So Rachel, you've been committed, I think, for your whole life. You were born with like some kind of a nuclear thing going on, I don't know, but you've been at it for a very long time. It's a great solution for a baseload option, but like, what are the latest like technologies and proven options that we have to, to go nuclear, which I think is what you want, us to at least consider as an option for this?
Yeah, there are a few different categories. What we have existing today are called large light water reactors. By large, I mean about 1 gigawatt, and by light water, I mean water. Nuclear people, we like to make it extra clear for people. So we have new large light water reactor designs. One actually just turned on in the United States in Georgia. They're being built more affordably and quickly in other parts of the world where they're growing quickly and they're good at building large projects. That is likely to continue. There are also what are called small modular reactors, and that's a pretty large basket of technologies that are similar in that they are more in the 50 to 250 megawatts range. Most of the parts and pieces can be factory manufactured and shipped to site, so you have little site customization, little on-site construction, so that the idea is in countries that are bad at mega projects like the United States, there's a much better chance we can build them on time and on budget. They also have significant improvements. Maybe they're very, very safe. All of these new designs can't melt down, so you can't have off-site consequences. So they're really being designed to alleviate people's concerns. Some of them are designed to burn up waste. They're all being designed for economic deployment. And then the third category that is a little bit niche but also interesting are called micro reactors. And they're really small, sort of the 1 to 5 to 10 megawatts. And those are, if you want to replace, remote diesel generators and provide microgrids. So if you're looking for electricity where it's actually really difficult to get fuel there and you can't completely rely on solar because it's sort of remote, it's solutions for those types of locations.
So part of what we talked about, we talked a little bit about like aviation fuel, right, which is a much harder thing to electrify giant airplanes. And so what are the alternatives that we have? Is there a kind of room for nuclear to play roles in like heavy industry where they need large amounts of heat? Or are there different types of solutions to deal with these, I don't want to call them edge cases because they all add up to, you know, every 2 or 3%. It turns out when you get 50 of those, it's like a lot. I'm pretty sure like all of it. So like, how do you eat away at that? And is nuclear one of the pieces in that puzzle?
It definitely can be. So nuclear, of the new reactor designs, they operate at a variety of temperatures up to 1,000 degrees. So you can't address the very hottest chunk of process heat, but you can address a lot of the range of process heat. And actually Dow Chemical is working with a company called X Energy, not one of our investments, to build a nuclear power plant to provide heat and power for one of their chemical plants. So there are starting to be these industrial partners. Nucor is one of the U.S. clean steel providers that is also working on sourcing nuclear power so they can continue to do electrified steel production cleanly and reliably. So some of these industrial partnerships are starting.
So if we've got to like swap out everything as fast as we possibly can, right? Why does it matter, Matt, like what order we do it in? Like what's the benefit of deciding that we're going to use all the technologies that we have today, scale them up as fast as we can? What's the benefit or what are we gaining by being smarter about, you know, where we deploy and what we deploy in those areas? Because it just seems like we've got to move really, really fast. So what's the, like, is it just all in as fast as we can go? Or is it, hey, we got to be smart about it and why?
We need to go all in and move very fast, but we do need to be smart about it as well. All of our models across more or less all of the different jurisdictions that we cover, and we have global coverage, show that in the transition to 100% clean electricity, the last 10% that needs to be decarbonised, more often than not, costs just as much as the first 90%. And that's where these dispatchable technologies are so important. So we see a future where the electricity system is predominantly supplied by wind and solar, but there is that 10% that needs to be dispatchable and baseload. And based on what we can see, you're not going to get that with existing technology. So a combination of wind, solar, and batteries, and that's where we need these other technologies to come in. And that's why we need to plan appropriately today, because everything in energy, it's infrastructure, so it's long life. So you build a solar farm now, it'll be with us for 20 years, and we'll be living with the consequences of that for 20 years.
Yeah, so these are long-term commitments that we're making.
Yeah.
So we've talked a little bit about sort of base load, and you brought up something that I think is really important for everybody to understand. And I would love an example because I've been looking for one, but there are very rarely is it the case that you have to have 100% uptime every time anybody wakes up in the morning and says, you know what I feel like I'm going to charge my EV today and plug it in. You heard earlier somebody saying, yeah, if that all happened in California, just wipe the grid out. But we've designed our electricity system to be that way, right? You need to have this, and the expectation is there. It's like expecting that every McDonald's or Starbucks is always going to be open at all times, right? That's not possible, and yet for electricity we have to do it. So you touched on storage, so I'm curious, and maybe both of you can touch on this. Where are we with having storage technology, right? We're flooding markets with intermittent generation. If those of you who are looking at the shape of the energy curves, like in California and Texas, we got a lot of solar going on, and that drives the price to negative in these markets. So we're going to need to bring storage on. Maybe we'll start with you, Richa. Where are we at the technology curve of, kind of long duration storage that's going to be able to play a role, whether it's tied to renewable energy or just sitting somewhere on the grid to allow for balancing and that reliability?
Yeah, so we have short duration, which is sort of up to 4 hours, and that's lithium-ion batteries. And they're pretty de-risked technologically, still fairly expensive. People project sort of where you think that can get to cost-wise, but it's unlikely it will ever be useful beyond sort of 4 hours, which is maybe you can shift lunchtime sun to dinner time demand when the sun is setting, but that's about how far you get. For long duration, what people are talking about sort of grid needs, and I'd love to hear your thought on this, in sort of the near term is up to 100 hours, so sort of a couple of days. So you can get through cloudy days, rainy days, days where the wind goes down. And there are actually quite a number of companies working in this area, and they're starting to have sort of like very first pilot deployments. And so there are sort of like Form Energy is kind of one of the more well-known ones. They're doing an iron air battery, so there are some chemical solutions. And then other people are doing storing thermal energy because it's sort of easy to store heat in some regards, and then using the heat to generate electricity. And that has the co-benefit of those same facilities can provide industrial process heat. So you have a dual use application. There are all kinds of combined heat and power demands, so they can service those.
That's awesome. Where do you see when you're looking at the asset locations and saying how does storage, you mentioned it, where does that play as a tool in that reliability equation?
Hugely important. What I would say, just to provide some more context, is that it depends on the country. So continent-sized countries such as America and China are much more fortunate in the sense that, in theory, if you can get the transmission built, you can get clean, variable, renewable energy to where it needs to go. And the bigger the country, the greater the possibility of matching supply with demand. I'm from the UK, which explains why I'm a lot paler than some other of you in the room. And what happens in the UK, more or less every year, is there'll be 2 weeks around January and February where there'll be no sun and there'll be no wind. And what that means is we need to rely on nuclear and gas because our coal's been priced out of the market. And that is a huge problem, and that I think is to Rachel's point about why long-term storage is needed, is because short-term storage will just never be economic to provide for that 2 weeks because it'll just cost too much.
So we have, obviously storage is getting advanced and that'll play an important role. From your standpoint, Rachel, you're looking at a lot of new technologies. Like, why shouldn't we just push all of our chips in on the stuff we have now and just go as fast as we can? Like, what's the benefit of continuing to invest in the hard tech and whatever technology you think is most interesting right now? Like, why bother? Why not just push everything in and getting what we have out there?
Yeah, there's a mix. So a few reasons. One, we should deploy what we can deploy today as fast as we can. And if we do that and then never develop a new thing, we'll kind of stagnate, and that's not that interesting. So people are developing new technologies that are more flexible, more useful, lower cost. So for example, Thermal Battery Corporation is one of these storage companies. They're able to store 2,600 degree heat. And so if they don't, that provides a real pathway to decarbonize the highest temperature process heat. And there's not like great other choices. So it's solutions for the things we don't have great solutions for, and it's solving the problems of existing things. So like geothermal is an example where we have some geothermal electricity. It's pretty expensive, it's sort of risky to drill. Fervo is a company that is revolutionizing geothermal, where they're improving the productivity and predictability of geothermal. So it's a resource that like we know about, but now we can make it much more useful.
Okay. All right, so I started this with saying all of you are going to get to put to work to solve all these problems. So I'm going to start with you, Matt. What's like the one thing that this group of get shit done kind of people should be doing to be smarter and get us like down that SBTI curve as fast as we can get there?
I'm going to go off on a tangent if that's okay. And
you have the mic.
And talk about you can't stop me. And talk about accounting, which is boring, but hang in there. The way companies account for their carbon emissions is progressively changing from annual to hourly, and I think that is going to have wholesale implications for investors and corporates, because what it will mean is you can not only get away with purchasing clean electricity, it needs to be available or dispatchable as well. And that's why it is so important. And I think, to your point, Scott, like additionality and this concept of additionality, we need people and we need investors, corporations to really make these markets and make sure that we are moving towards an electricity system where we're investing in those technologies that will make sure supply and demand balance.
Cool. All right, Rachel, what should everybody do?
Yeah, so to meet these sustainability requirements and to actually get hourly clean energy, become a customer. So many of you work for corporations that make choices in what you build, what you buy, what you purchase. So for these companies that are trying to scale, once their technology is proven, they need to sell to customers. And so sign offtake agreements. Go try out some of these new products, even if it's at a pilot scale or sort of a first or second commercial choice. That's kind of how this stuff gets really into the market and gets over the hump so it can be low enough cost to win the day.
Awesome. So be a pioneer and get ahead of the curve a little bit. I'm really grateful for both Matt and Rachel for being here, so thank you. Give us a round of applause and we'll get out of here. Thanks, everybody.